Hello, my name is Jackson Motley, and I'm an undergraduate mechanical engineering student here at Iowa State University. I focus on wire arc additive manufacturing, utilizing this technology in combination with collaborative robots to push the boundaries of modern manufacturing techniques. This semester, I focused on the effects of longitudinal arc oscillation during collaborative robot-assisted wire arc deposition. I am pleased to have worked on this research with Mohammed Arjomani and under the direction of Tuan Mukherjee. Today, I am very excited to share my work with you on research in longitudinal weaving, a wire arc additive manufacturing process that offers many implications within metal 3D printing. Before we get into the research, we should first go over what wire arc additive manufacturing, or WAM, is, as well as its advantages and disadvantages. Wire arc additive manufacturing is an advanced manufacturing process that utilizes electrical currents to deposit metallic materials layer by layer, similar to the welding process. This innovative technique offers several distinct benefits. WAM is highly efficient, minimizing material or energy waste when compared to traditional manufacturing methods. The process also enables the creation of parts with near net geometry in just one step. WAM is particularly advantageous for producing large-scale components in a short amount of time, as its cost-effectiveness for individual parts sets it apart from other manufacturing methods, as its scalability makes it ideal for one-off or low-volume production. However, WAM can also come with challenges. The process is highly vulnerable to significant warping and residual stress, which can be caused by high heat input. There is low inherent dimensional accuracy, as precision is often a trade-off, causing a possible need for additional finishing steps. The effective use of WAM also requires careful planning and design considerations to account for thermal effects and structural integrity, leading to high production time. Finally, while WAM is effective for simpler designs, intricate or highly detailed shapes may exceed WAM's capability, as there are several limitations on complex geometry. By understanding both the advantages and challenges, WAM can be leveraged to effectively meet the needs of various industries. A critical issue in the WAM production process is humping, a common defect that significantly impacts the quality of the final product. An example of a case of humping can be seen within the top right picture, and a more extreme case within a single track can be seen within the bottom picture. Humping disrupts the intended shape and precision of the finished part, while also compromising structural integrity. This lowers the hardness and component lifespan, as well as affects the surface finish of the part. Addressing the humping defect is a critical step to improving overall quality and performance in manufacturing applications of WAM. It's hypothesized that the utilization of oscillation techniques during the deposition process has the potential to significantly enhance the quality of the final product. By introducing controlled oscillatory motion, the heat distribution becomes more uniform across the substrate, reducing thermal gradients and minimizing residual stresses. Additionally, this approach facilitates a more even dispersion of material, improving microstructural integrity and promoting consistent layer bonding. These benefits collectively contribute to superior mechanical properties and dimensional accuracy in additively manufactured components. The experimental design first focused on three distinct cases to systematically analyze and address the effect of longitudinal weaving on the occurrence of humping in wire arc additive manufacturing. Case A, or the perfect weld, was used to establish an ideal baseline with little to no defects and used process parameters outlined in previous research. Case B systematically introduced humping within the track deposition in order to study its characteristics and impacts on the track. Case C aimed to find a reduction in humping by introducing longitudinal weaving, looking for a minimization or elimination of the humping defect. These results were obtained through trial and error, followed by precise validation using confocal microscopy to ensure accuracy. The second series of tests were held to compare the effect of oscillation amplitude on a given parameter, such as scan speed, voltage, or wire feed rate. A total of 3 sets of 25 tracks were examined under varying conditions to provide robust data. This approach provides valuable insights into how process parameters may influence the formation of the humping defect. These results were then qualitatively compared to draw conclusions about the development of humping and possible optimized manufacturing techniques. Here we have case A, dubbed the perfect weld, and some of its associated parameters. Many parameters, such as wire diameter, voltage, wire feed rate, cool time and fill time, as well as angle from substrate, will not change throughout this portion of the testing process. Unique to this case are the travel speed, also referred to as scan speed, parameter of 7 millimeters per second, as well as the fact that there is no inline weaving. As you can see within the picture, this case has a very smooth surface finish, with a consistent height throughout the deposition. On to case B, and you'll notice the only parameter to change is the travel speed, raising from 7 to 13 millimeters per second. As you can see within the picture, this case contains many common effects of humping, having several peaks and valleys, as well as highly inconsistent height throughout the track path. Finally, we move on to case C, where we have started introducing longitudinal inline weaving to the deposition process. Like case B, the travel speed is 13 millimeters per second. Important things to notice are the reduction in severity of peaks and valleys, as well as a more consistent average deposition height. While this case does not represent a complete removal of humping, the obvious reduction of the defect leads to a strong implication that introducing inline weaving will lead to higher quality depositions at higher speeds. Here, we can see some of the important results of the second phase of testing, where we aim to compare amplitudes and its effect on key process parameters of a WAM. This graph is a representation of 25 tracks, where dots within the red region contain a significant amount of humping. Tracks found within the green region contain an acceptable level of humping. On the right, we can see 5 tracks, which are circled in blue on the graph. These tracks display how a given scan speed, in this case 9 millimeters per second, is affected by several amplitudes, with an acceptable level of humping first occurring at the amplitude of 8.25. Tracks B and C are also marked on the graph and represent the worst and best tracks respectively. The next parameter tested was voltage and how it is affected by several amplitudes. The 5 highlighted tracks occurred at a voltage of 12.1, with an acceptable level of humping occurring at an amplitude of 6.25 millimeters and below. The worst case of humping, track B, now contains a discontinuity, another side effect of humping within a single track deposition. The final parameter tested was wire feed rate. The 5 highlighted tracks occurred at a feed rate of 169.34 millimeters per second, with an acceptable level of humping once again occurring at an amplitude of 6.25 millimeters and below. An extra parameter that has an effect on deposition quality is the torch angle. This was discovered during the testing phases. To finish the data collection, 5 tracks were made to study the direct effects of torch angle on track integrity. The pushing technique, in this case 60 degrees and 75-degree angles, directs the arc away from the molten pool. This promotes a broader heat-affected zone and uniform temperature distribution, which results in a narrower and shallower bead, creating enhanced bonding between layers. This is favorable for most applications. The pulling technique, 105 and 120-degree angles, directs the arc towards the molten pool, increasing thermal gradients and causing track discontinuities due to uneven heat distribution. A 90-degree oscillation angle balances these techniques, offering a combination of heat distribution and ensured track integrity. The results of testing this semester show that longitudinal oscillation can improve track integrity at high scanning speeds. This indicates the effectiveness of longitudinal oscillation to support increasing productivity without affecting product quality. Although longitudinal oscillation is beneficial, the oscillation amplitude needs to be selected based on other process parameters to avoid track discontinuity. For example, very high amplitudes at low wire feed rate can disrupt the continuity in metal deposition, degrading track integrity. Higher voltage can cause instability, leading to irregular molten pool shapes that result in inconsistent deposits and defects like track discontinuity. However, The heat input from lower voltage with higher amplitude allows for a wider molten pool, promoting a larger contact area for fusion and thus improved track integrity. Finally, adjusting torch angles revealed that pushing angles reduced localized overheating, while pulling angles can cause track discontinuities due to disturbances in the metal deposition. Additionally, a 90-degree oscillation angle provides balanced heat distribution and improved track integrity. This research experience has provided me with valuable insights and skills that will extend beyond the immediate study. Some main takeaways are that I learned how to optimize workflows and address challenges systematically. I've gained hands-on experience with experimental design, data collection, and analysis, leading to a deeper understanding of scientific research. I also strengthened essential career skills, such as presenting findings effectively to various audiences, as well as time management, as I had to adapt schedules to accommodate unexpected challenges while maintaining progress. For future plans, I plan on continuing research with Dr. Mukherjee, furthering investigation of oscillation in wire arc additive manufacturing. This will be completed through advanced coursework, including ME 490T and 490H projects. I am also considering a future in academia, with plans to pursue a master's program as a potential next step in this academic journey. To wrap it up, I would once again like to extend gratitude to Dr. Tuan Mukherjee for providing me with this amazing opportunity, as this work has laid the foundation for both personal growth and professional development in the field of engineering research. Thank you.